Hi students, today we will be discussing the topic metals and nonmetals extraction. Okay, metals extraction only we will be discussing in this video. So to extract a metal, we should know where we can find them. Okay, so we know that earth crust is the major source of metals. They are found in the free state or in the compound. And seawater. Another also contains soluble salts such as sodium and magnesium chloride. So elements or compounds which occur naturally in the earth's crust are called minerals. So what are minerals? They are actually metallic compounds. Then what are ores? The mineral from which we are extracting the metal. That means the mineral will be in a very high percentage in the ore. Okay. Or the mineral from which we are extracting the metal is called the ore of that metal. Okay, so in the nature we can find many compounds, but we'll be selecting one or two as an ore, depending upon the ease of preparation or the availability or the concentration of the metal in it. Okay, considering the factors like that. Then these are all pictures of minerals given here, and before starting the extraction, we should know, we learned this reactivity series. We can divide the reactivity series into three categories. First category is highly reactive. Potassium, sodium, calcium, magnesium, aluminum, they are very reactive metals, where the others, zinc, iron, lead and copper, are medium reactive and low reactive metals. So metals of low reactivity, metals of medium reactivity and metals of high reactivity. These are the three classifications for the metals according to the reactivity. Okay, and ores of many metals are oxides only, because oxygen is very reactive and is very abundant on the earth. So many of the ores we can find will be in the oxide form. Okay, now this is the rough picture, or it gives overall conversion of an ore into a pure metal. Okay, so once we have the ore with us, the first step we had to do was the concentration of the ore. Then for the metals of high reactivity, we use the help of electrolysis, or we use the help of electricity to separate the metal from the ore. We are getting the pure metal there. Okay, so no purification there, only electrolysis. And metals of medium reactivity, either in the carbonate form or in the sulfide form. Okay, and in both the cases we'll be heating it. If it is carbonate ore, we'll be doing heating in the absence of oxygen, whereas sulfide ore will be heating in the abundant supply of oxygen. Roasting it is called. So carbonate ore will be calcinated, whereas sulfide ore will be roasted. Okay, both results in the oxide of the metal. Now what is remaining is reduction of the oxide into the corresponding metal. Then the last step is purification or refining. Okay, then metals of low reactivity are usually in the sulfide form. What we have to do is only roasting. You'll be getting the metal. No need of reduction, keep in mind. And the last step is refining. This is the rough picture. We'll be discussing it one by one. Okay. So the first step we understood it is enrichment of ores. Means we are increasing the concentration of the ore by removing the gangue. Gangue means the unwanted substances present in the ore, such as soil, sand, etc. Gangues are removed by various separation techniques based on the differences between the physical and chemical properties of the gangue and ore. Okay, so if the material is a magnetic material, we can use the help of magnetic separation. See, the magnetic separation will be passing the finely ground ore through a setup like this, in which we are having a magnetic roller here. So which will be attracting the magnetic material from the finely ground ore, and that substance will be separated. Others It will be the gang will be separated. So thus we can separate or get the magnetic material ore like this, in a concentrated form like here, like this. Here is why hydraulic washing is given. It is by the power of, see, water is pumped through, water current is and will be flowing, allowing the fine particles of the ores to fall down, and through which they are passing a current of water, and the lighter particles will be moving along with water, whereas the heavier particles, that means metallic ore, will be coming down. So depending upon the impurities, depending upon the metal, we can select different types of enrichment methods, okay, like magnetic separation, hydraulic washing, etc. Now, first we'll talk about extracting metals of low in the activity series. We have a mercury and copper is being discussed here. Mercury is available, or it is found in the nature in the form of sulfide, or we call it cinnabar. Cinnabar is mercury sulfide, ore of, that is ore of mercury. Okay, so heating in the air first converted to mercuric oxide. So this is the reaction. This reaction gives the extraction method. So we'll take the ore cinnabar, heating in the air gives mercuric oxide. Further heating gives you mercury. It decomposes. Mercuric oxide decomposes to get the mercury like this. See, this is cinnabar, first heated, then further heating gives you the metal mercury. Okay. Now the next is copper or copper sulfide. It is cuprous sulfide actually. So in heating, that also we are simply heating only. They are low reactive. But the reaction taking place in the case of copper ore is different from that of mercuric sulfide. Okay, this copper sulfide ore will be heated in abundant supply of oxygen. It forms its oxide together with the release of sulfur dioxide gas. Then what happens is the copper oxide formed will be reacting with the remaining copper sulfide to get, and a redox reaction taking place, and we are getting the copper metal get separated. Okay, so this is what is happening inside. In both the cases, what outside we are doing is only heating. Here the oxide is forming, oxide decomposes. Here the oxide forms, react with the remaining sulfide to form the metal. Okay, in both the cases we are doing the heating process only. See, this is copper oxide, copper sulfide. Heating, we are getting copper oxide. Then it becomes pure copper metal. Okay, so that is metals in the low activity series. Okay, mercury and copper sulfide is given in the text. Then middle of the activity series, extracting metals in the middle of the activity series. They are also present in the form of sulfides as well as carbonate in nature. So here they have given the example zinc. Zinc is available in the form of sulfide form as well as in the form of carbonate form. So zinc sulfide and zinc carbonate. So if it is zinc sulfide, we will be roasting it. Roasting means heating in abundant supply of oxygen. We are getting zinc oxide. But if it is carbonate, it will be calcining. We will be doing the process called a calcination. What is that? Heating in the absence of oxygen results in the formation of zinc. So both results in the formation of zinc oxide. Okay. So this is roasting, this is calcination. Sulfide ore is roasted, whereas carbonate ore is calcinated. Both gives you zinc oxide. Okay. Now what to do? Reduction process. We have to remove the oxygen from that. We can do that with the help of carbon. So zinc oxide is reduced with the help of carbon to get the zinc metal. So this is what is happening to get the metal. But this metal is impure, we know. It should be purified. Okay. But before going to that purification method, we have some more examples given here. See, the reduction is, and we are using the reduction process in for some other purposes also. Okay, reduction is also possible by displacement reaction. That means zinc oxide, if you use a more reactive metal, also we can displace zinc from the zinc oxide, right? The example is given here, manganese dioxide is from manganese dioxide we can get the metal manganese by reacting it with a more reactive metal aluminium. Okay, we are getting the metal manganese, aluminum oxide. Okay, along with the liberation of heat. Of course, displacement reactions are exothermic, we know, isn't it? And there is an application for this displacement reaction. Since these displacement reactions are highly exothermic, the metals produced will be in the molten state. So if you take iron oxide and aluminium, we will be getting iron in the molten form. Why? Because the displacement reaction is exothermic. Okay, so it makes the iron formed to will to be in the molten form. So this reaction can be used for welding purposes in to join railway tracks and okay, that process or that reaction is called a thermit reaction. So what is thermit reaction or thermic process? This is a displacement reaction by aluminium, okay, of iron oxide with the help of aluminium. Iron will be getting in the molten form, and so since it is in the molten form we can use this reaction to weld to join railway tracks and all. Okay, so that process is called, or that reaction is called thermit reaction. Now the coming to the metals towards the top of the activity series. Okay, sodium, potassium, aluminum, magnesium, and calcium. Okay, they are the top reactive elements, and we need the help of electricity to separate the metal from their ore. Okay, these metals are obtained by electrolytic reduction. Sodium, magnesium, and calcium are obtained by the electrolysis of molten chlorides. Okay, and see what we have to do is we have to take see for example what is given shown here is extraction of sodium from the ore sodium chloride. So we have taken molten sodium chloride as an electrolyte. Remember, sodium chloride will be having not aqueous, it is not aqueous, only molten form. So only two ions will be there in the electrolytes, Na plus and Cl minus. Na plus being cation will move towards the cathode, Cl minus being anion will be moved towards the anode. Okay, so sodium metal comes and takes electron from the cathode, form the sodium metal and will be deposited, will be settled down there, whereas chlorine gas will be escaping along on the anode. Chlorine gives out one electron and forms chlorine atom, and two chlorine atoms combine to form chlorine molecule. Okay, so that is extraction of metals in the top of the activity series. They are made by electrolysis. So what is special about this? The metal we are getting will be in the pure form. So we don't have to do further purification. Now, refining of metals in the other cases for the medium reactive metals and all, and the low reactive metals can be or should be purified before using it. That is done by the help of electrolysis. So what we have to do is we have to take the impure metal as the anode and the pure metal of the same metal as the cathode, and of that metal salt solution. If it is copper, copper sulfate solution, or if it is silver, silver cyanide, like that. Okay, so whatever be the metal, that metal salt solution should be the electrolyte. Okay, then after some time we can see that once we pass the electricity through it, we can see that the pure metal from the anode will be moving towards the cathode and will be getting deposited over the cathode, and the impurities present, it will be coming down and will be formed as a anode mud. This is called the anode mud. After electrolysis we can find the anode mud below the anode. Okay, so keep in mind impure metal as the anode, pure thin sheet of metal as the cathode. Okay, then See, it is this is the diagram given in your text, but the anode and cathode is kept reverse over there. So keep that. On passing the current through the electrolyte, pure metal dissolves, okay, from the anode and goes to and go and get deposited at the cathode. Electrolyte is acidified if it is copper sulfate solution. Anode impure copper, cathode pure copper will be deposited at the cathode. Now, once we get the pure metal like this, either by electrolysis or by the extraction at the top of the reactive series, there is a chance for corrosion. Okay, corrosion means losing the metal. They are really combining with the surrounding gases, form the oxides or sulfides like that. Okay, so see here it is silver articles is getting black color after the coating of silver sulfide. Iron gets rusted. Copper gets a copper green coating over the surface like that. Basic copper carbonate it is called. See, iron is forming iron oxide on its surface. See, this silver got silver black color due to silver sulfide. Copper got its is getting its green color due to basic copper carbonate. Iron gets brown in color due to rust formation. Okay, so this is uh, something to be avoided. To avoid corrosion, we can we have to find out what is the reason for the corrosion. For that, there is an activity given here, and in that activity, it is showing the first case there is moisture is there, air is there. The second case there is moisture but no air. Third case there is no moisture, no air. So in both the cases, we don't have the iron nail is not getting rusted. That means only air, no moisture. But in this case, air is there, moisture is there. In that case, we can see that the iron is getting rusted. So the condition for rusting is air and presence of air and moisture. So if to avoid that, the presence of air and moisture, if you can avoid, you can avoid the corrosion. Okay. So that is the technique. Based on that, we have developed many methods to avoid corrosion, to prevent corrosion. Number one is painting, oiling, greasing, galvanizing, chrome plating, anodizing, or alloying. These are the main methods used to prevent rusting of iron. Galvanization, first one. Okay, galvanization is the coating of steel and iron with a thin layer of zinc. Okay, to protect from rusting, steel and iron can be galvanized using zinc. Okay, we are doing a coating, depositing a coat of zinc over the metal. That is called a galvanizing. See, this is will be the galvanized steel. Okay, then see greasing. Apply we it is done in vehicles and painting. In many cases we can find painting. Oiling also we can find in many places, right? So chrome plating. So these are all different types of methods to prevent corrosion. Okay, now alloy. Alloying is another method, that is addition of other substances. It can be a metal or a non-metal to a metal to get a new desired substances. For example, the definition is given here. A homogeneous mixture of two or more metals or a metal and a non-metal is called alloy. It's a homogeneous mixture. Okay. For example, it is given examples of alloys. Pure iron is mixed with the 0.05% of carbon. We get a steel. Okay, we get steel. Then mixing iron with nickel and chromium forms stainless steel. Pure gold, we know it is 24 karat gold, is very soft. So not to make it hard, we are adding silver or copper, making it 22 karat gold. The remaining two parts will be of copper or silver. So 22 karat gold. These are examples of alloys or alloy. What is advantage? Making it more hard, more durable, less corrosive. Okay. Then another example is amalgam. If an alloy contains mercury in it, we call it an amalgam, which is used to amend teeth and all. Then brass, another alloy of copper and zinc. Bronze, alloy of copper and tin are good conductors of electricity. Are not good conductors of electricity. Okay, so alloys are not good conductors of electricity, unlike the components, unlike the components from which we have made the alloy. Solder, another alloy of tin, lead and tin, has lower melting point, unlike the metals used. Okay, then and we know it is used for welding electrical wires and okay. So these are bronze, another alloy, solder, brass. These are all examples of alloys, and the components are also given here. We have to keep by heart. We have to study the components and of all the alloys. Then there is a wonder of ancient Indian metallurgy. The iron pillar, built 1600 years ago near the Qutub Minar in Delhi, has high quality of rust resistance. It is 8 meter high and weighs 6 tons. Even now, it remains uncorroded. No corrosion is not affecting it. Okay, so that's all in this video. The next video will be talking about reaction between metals and metal and non-metal. Okay, thank you.